will continue the discussion here. There is a concept called TCP fast retransmit. Yesterday, we looked at one of the scenarios where we faced something called cumulative acknowledgement. Okay, there were 2 packets sent with different size, different number of bytes. All right. So when the first packet has been received and the acknowledgement is sent, but it is lost in the middle. But the second packet also has been received, but its acknowledgement is received properly. We call it as cumulative acknowledgement. Okay? Hope you remember that. Now, what is that fast rate transmit? Because we also are discussing a lot about the TCP timeout. Yesterday, we looked at how we can arrive at the TCP timeout value. And we also know that still the good research is going on to get the optimum value for timeout. TCP also has attempted various parallel mechanisms to improve the performance in terms of latency. Okay, the latency has to be reduced. So what is happening in that case? When there is a segment is lost, okay, you are not going to get the acknowledgement. All right, and if you have you are supposed to receive, you are on the receiver side. Okay, you are supposed to receive 3 packets, maybe with the sequence number 100, 200, and 300. You are supposed to have received till 399. Okay, if the size of each packet is 100 bytes. Unfortunately, the third packet is lost. You have received only till 299. All right. So your acknowledgement would be 300. All right. And you have received the 400th packet. Still, you will send the acknowledgement of 300 because the 300, the packet with sequence number 300 is not received by you because it's lost in the middle. So you would send the duplicate acknowledgement of recently received continuous packet. Okay. So when the sender is receiving from the receiver, okay, I'm the receiver, I'm sending you the acknowledgement for the recently received packet, which is correctly received without any missing packets. In that case, when the sender, okay, who has already sent the packet, receives 3 acknowledgements for the same data, that is called a duplicate acknowledgement. When the sender receives 3 duplicate acknowledgement, he understands that, okay, the data packets, whatever I have sent after this has not been received by the other person. So it will go for retransmission. It will not wait for the timer to expire. You got it? All right. So this is called TCP fast retransmit, one of the methodologies to improve the latency parameter. Okay. The same thing is given as the example here. Fine. First packet with sequence number 92 and 8 bytes of data has been sent. Second packet with sequence number 100, but having 20 bytes of data is on the way, but it is lost in the middle due to some reason. So the host B has sent the response for this. Okay. After that, without knowing that, using the parallelism, the sender has sent the third packet. Could you see that? Probably I'll use a pen here. Yeah. You see this? The third packet also has been transmitted. This could be 120 if the size is 10. So this could be 130 and so on. So it sends the third packet, fourth packet, and fifth packet as well. But in the meantime, it has received the acknowledgement for this. It hasn't received the acknowledgement for this because the packet is already lost. Now, when you, as soon as you have sent this packet, what is expected by the host B? Host B is waiting for a packet with sequence number 100. But what has been received? Yeah. It has received only till 99. Okay, 92, 93, 94, 95, 96, 97, 98, 99. So only till 99 it has received. It is awaiting for the 100th, the packet with sequence number 100. Okay, so it is sending the 100. It has sent the 100, but it hasn't received. So it sends the acknowledgement with the number 100, waiting for the packet with sequence number 100. Okay, and then by the meantime, it has received another packet with sequence number 120, then 130, for instance, 140. However, host B is unhappy. Okay, it says, boss, I was waiting for packet with sequence number 100. So it sends the acknowledgement for 100 3 times. So once you get the duplicate acknowledgement for the same packet 3 times, the TCP sender retransmit this packet. Could you see that? It retransmits. This is called fast retransmit to improve the latency. Okay, this is one of the interesting phenomena which is happening in TCP. All right, so this is about sequence number, acknowledgement number, retransmission, how the TCP is handling the duplicate packet, the duplicate acknowledgement, how it is interpreted, what's happening in the case of fast retransmit, and so on. The next major expectation from TCP is flow control. We will not talk about flow control in in the UDP protocol. Okay, so in a nutshell, what is a flow control? Probably I have put a point here. This can help you in understanding. Okay, the receiver controls the sender so that the sender will not overflow the receiver's buffer by overwhelming the data too much. Very simple. I told the example on the other day. When suppose you are able to take down the notes, let's say 50 words per minute, okay, just for instance, okay, or 25 words per minute, I'm just saying. So per minute you can write down only 25 words, but suppose I'm giving you notes and I'm dictating at the speed of 40 words per minute. You are not going to take it up, because you will not be able to take it, because the speed at which you are taking down is slower than the speed at which I am dictating to you. So you would say, sir, please slow down. Okay, I'm not able to take up, you please slow down this pace. So then I will reduce the pace. Probably I will reach somewhere around 25 words per minute. Now you are convenient, you are comfortable. Okay, who is controlled? The teacher is controlled. By whom? The student. Similarly, the receiver controls the sender, that boss, do not send this much data, it's too much for me to take up. All right, this is called flow control, just to see that the receiver is not overwhelmed by too much of information, too much of data or the packet from the sending side. Okay, this is what happening in the case of flow control. Now the question is, how are you achieving flow control? Very simple. You got a field called receive window. Is it shown here? Yeah, you got a field called receive window. Probably I'll go somewhere to the yeah, here. Could you see that? Yeah, this is called receive window field in the TCP header. Okay, so this field is going to help you in your so that is the receive window field. Where are we? We are somewhere here. Yeah, so this is the receive window field, which is of 16-bit in size, that tells the sender that how much space it is having, so that the sender can send only that much byte of data. Very simple logic, sir. I'm telling, sir, I have only small room, only one person can come. Or I can say, I have a big hall, 25% can be accommodated at a time. Something like that. Okay, this is called the receive window field. This, if you read this line, that will help. Okay, the receiver advertises, doesn't mean advertise, actually it is telling the sender. The receiver tells the sender the free buffer space by including the receive window value in the TCP header of receiver to sender. So as the receiver, I'm telling the sender, I'm setting the value in the receive window, which indicates the sender that that is the amount of space this fellow is having. This is the logic, no other complexity in understanding this. Okay, hence the sender limits the amount of data to the receiver. It will be limited to RWND, that is receive window size. Okay, it guarantees that receive buffer will not be overflown. That's it. This is what your flow control. Okay, then comes the congestion control. Flow control logic is very simple. All right, but what is happening in the case of congestion control? We got one interesting statement here about the flow congestion control. Too many sources sending too many data or too much data too fast for network to handle. Okay, but what was happening in the previous one? Probably I'll go here. Okay, here the sender will not overflow the receiver's buffer. This talks about the sender and the receiver. But when we are talking about the congestion control, I'm not talking about the sender and the receiver. Rather, I'm talking about the network. That's why it's highlighted here. All right. So congestion control, the similar logic, but on the network. So think of congestion control process as the traffic constable standing at the four-way junction regulating the traffic. Right. So probably let's say east to west and south to north. Okay, these are the four roads. They are getting no, they are meeting somewhere at the junction. There is a traffic police standing and he is regulating the traffic. Okay, probably he can say if there is too much of traffic coming from one side, probably he would permit that to go. The other person have to stop. If he is overflowing, okay, you can stop here. You can come from the other side. Something like that. Okay, so this is called congestion control. So reducing the traffic jam at junctions. All right, very similar to that in the network. At the network, there should not be too much of information sent by too many people at higher transmission rate. Congestion control. Okay, this is not flow control, though some of the people in few of the textbooks reference books I have seen flow control and congestion controls are used interchangeably. That's not true. Flow control is between the sender and the receiver, but congestion control is at the network. Okay. So the manifestation, how can we understand that there is a congestion control? Packet loss and packet delay. Okay. But at the same time, you also should be careful that you should have some measures to differentiate congestion control from denial of service attack. Right? I can give you one example. Probably the results are announced on a particular day, probably at evening 7 o'clock, let's say, and everyone would be trying to log into the system of COE portal to see the results. Everyone would be attempting. Okay, at that time it would be relatively slow. Sometimes you may get an error called page cannot be displayed and so on. This is what the exact example of congestion. Okay, what is the denial of service? Denial of service is an attack. It is a specifically designed or probably deliberately made attempt that you will not be able to access the resources which you are entitled to access. That is called denial of service attack. All right, so do not confuse denial of service attack with congestion control. We talk about congestion control. Okay, so the packet loss and packet delay, these are some of the measures by which you can understand that there is a congestion. Okay, so what are the different causes of congestion? This is out of syllabus from your textbook, but I thought I should explain to you using this. I'm probably going to quickly run through. Okay, we got some 4 people, host A, host B, and C and D. Okay, there is a router which is having infinite buffer, which means 1000 MB, 200 GB, 1 terabyte, no problem, I can accommodate. Okay, so this is going to be infinite buffer it's going to have. Now, there are 2 people. Host A is communicating to host C, and host B is communicating to host D. Okay, these are the 2 communications which are happening through the same link. The router is having probably the transmission rate of R, for instance. Okay, now what will happen? Okay, you got lambda in. Lambda in indicates the amount of data which is sent across the link. So he will be sending lambda in. And what is lambda out is the throughput. Throughput is again the measure of how much data packets have been received to the ratio of how much data packets have been sent. That's the throughput. Throughput is always going to be in the range of 0 and 1, between 0 and 1. You can reach up to 1, probably 0 also can be a throughput. All right, so that is called lambda out. Obviously, lambda out is going to be lesser than or equal to lambda in. You got it? Okay, that is called your the measurements which are given here. All right, so you are drawing a graph. Okay, as you increase the lambda in, as you increase the data, because this bandwidth of R is shared by 2, you can go up to a maximum of R by 2. Why? Maximum bandwidth is R, and because there are 2 links, 2 communications happening in parallel in the same link, the maximum available bandwidth is R by 2. So as you are increasing, whatever may be the data rate which you are having, you cannot send something beyond R by 2, because that is the maximum realizable bandwidth for a single communication. So maximum per connection throughput is going to be only R by 2. What is the problem, sir? There is no problem. But what about the delay measurement? Yeah, delay measurement is giving something interesting one. What is that? Lambda in, as it is increasing, delay is slowly going up. Okay, so you remember there is a formula called L by R, probably L multiplied by A. LA by R is the traffic intensity. This traffic intensity is supposed to be less than 1. It is not supposed to be even equal to 1 or greater than 1. Okay, so as you are increasing, as you approach R by 2, you might have seen a very similar graph in the case of loss. So your buffer is infinite, no loss. Okay, one router, infinite buffer, capacity is capital R, no retransmission. Every data is only original, because we don't talk about loss so far, but there will be a huge delay. Okay, why should I talk about delay, sir? Look at the previous table or previous screen. Long delay is also a manifesto of your congestion control. So if there is a delay which is increasing exponentially, could you see this? It is increasing exponentially. As it is increasing, this is the manifesto of the existence of congestion in the network. Okay, so similarly, there are a lot of other scenarios are also available. I invite the interested readers to please read the textbook. The same thing is available with Cross and Ross to know more about this. Okay, so slowly the complexities are involved and some interesting measurements you can see. Okay, I comfortably skip it because it will take a lot of time to explain, which is again out of the regular syllabus. Okay, but if any one of you are very much interested, let me know. I can handle special class on this to know more about the congestion. Okay, now you could understand congestion. I have spoken about the case of the existence of delay, and then which is the indication that there is a congestion. It also will lead to loss of data. So delay and loss are the good indicators that there is a congestion. Okay, now what does TCP do to avoid the congestion? Okay, there are two things. Okay, one is end-to-end congestion control that is taken care by TCP. Okay, what is that end-to-end congestion control? Network will not bother. Network will function as usual, but the TCP will indicate the center. TCP will initiate some congestion control mechanism, which I'm going to show you how it is going to happen. All right, this is TCP initiated end-to-end congestion control. What about the second one? That is network assisted congestion control that is taken care by the routers or the layer 3 switches in the system, in the network. So they are available in the network. So they provide indication to the system. Boss, you are sending too much. There is a huge traffic in the network. Okay. The best example of network assisted congestion control is ECN, early congestion notification. Dear friends, please spend time by your own to read about early congestion notification called ECN, then random early detection, RED, then drop tail mechanism. These all are interesting congestion control mechanism available in the network to thwart or at least to mitigate the congestion which happens in the network. Okay, so please read about this interesting novel kind of procedures. Okay, you will really fall in love with how the design is made to not avoid but to manage the congestion in the network or to control the congestion in the network. Okay, but let's focus on TCP congestion control. Okay, two things. It is called AIMD. What is AIMD? Additive increase, multiplicative decrease. Very simple, sir. I'll tell you the logic behind this. You will easily understand. Logic is very simple. Initially, I'm sending 10 packets. Okay, I'm giving some vague numbers and simple example. I'm sending 10 numbers of packets. I don't get any congestion notification. So I will go 11 packets. Then I will send 12 packets. Let me say bytes, 13 bytes, 14 bytes. Slowly I'm increasing. This is called additive increase. For every transmission, I increase the number of bytes by 1. Okay. And then suddenly there is a congestion. You know, recently I have sent 48 bytes, but I got a congestion notification. Then I'll go for multiplicative decrease, which means if I have sent 48 bytes, I will reduce my speed to half. Okay, so I will reduce to 24 bytes. If there is congestion, no, I'll go to 23, 24, 25, 26, 27, and so on. Suppose I reach some particular number and there is a congestion, I will reduce the speed into half. This is called additive increase, multiplicative decrease. Logic is very simple. You can see a sawtooth behavior in AIMD. Okay, very interesting phenomena in TCP congestion control. So AIMD, additive increase, multiplicative decrease. You can see a sawtooth behavior for congestion control. I think you can see that graph here. Yeah, see there is an increase, but suddenly it is reduced to half. It comes here, and then slowly it is getting increased to some place. And you see there will be a congestion. Then it will be, what is the distance here? So it is supposed to be dropped here. Okay, and then you will slowly increase. So this is how, okay, this is how you will reach something called sawtooth behavior in the case of AIMD, which is an interesting one phenomena in TCP congestion control. Okay, so what is additive increase? Increase the congestion window by 1 MSS. What is the MSS? Maximum segment size dictated by the network layer and the transport layer. Every RTT means for every cycle of communication. So I send 20, 21, 22, 23, and so on. Okay, when there is a congestion, I will reduce the CWND into half. So CWND becomes CWND by 2. Okay, and then slowly it increases. This is called additive increase, multiplicative decrease. Second one is TCP slow start. Okay, when connection begins, this is another one. When the connection begins, what is that? I have just established the connection. All right, I will increase the rate exponentially until first loss event. So initially I'll make it as 1 MSS, then every RTT I will make it double. So the congestion index becomes double, which means I send 1, then it becomes 2, then it becomes 4, then it becomes 8, and so on. Okay, this is slow start. Again, when there is a congestion, you are going to reduce it by 2. Okay, so this increases speed. So it is not AIMD, it is slow start. Okay, so these are the 2 congestion control mechanisms which we have in transmission control protocol. Right.